In this video, I will describe the extension system architecture of Kunkun. This video will be relatively technical, so feel free to skip if it's not for you. However, since most of you are likely programmers, this should be right up your alley. Docker is a popular containerization engine. It runs on top of the operating system, while containerized applications run on top of Docker. All containers share the host operating system's kernel APIs. Kunkun functions similarly to the Docker engine. It is a desktop application that hosts extensions. Extensions running on Kunkun can access system resources and APIs through the app. Unrestricted extensions pose significant security risks. When you install a desktop application, you usually trust its developers. But when installing an extension within the app, you might relax your defenses. Can you really trust the authors of every extension? Extensions could contain malicious code designed to steal sensitive data or control your computer. Even without malicious intent, supply chain attacks embedded in dependencies can be difficult to detect. To mitigate these risks, it is crucial to sandbox extensions by default for maximum security. Currently, Kunkun's extensions run in web workers or iframes. Web workers handle lightweight script-based tasks and GUI with templates, while iframes support extensions with complex or custom graphical interfaces. Both are sandbox environments provided by web technologies, making them safer than running extensions with Node.js. However, with great power comes great responsibility, and conversely, sandboxing limits features. The most you can do is implement embedded web pages. To address this, Kunkun provides numerous APIs, including clipboard access, file system operations, shell commands, system information, and much more. Developers can call these APIs directly using JavaScript or TypeScript, enabling the creation of robust features. Extensions communicate with the main Kunkun app via a custom protocol called KRPC. API requests from iframes or web workers are executed by Kunkun, which then returns responses over KRPC. If extensions can access all system resources, what's the point of sandboxing? This is where permission control comes in. Extensions must declare the permissions they need in their manifest file. Without proper declarations, API requests will be denied. For example, if an extension needs to read clipboard text and access a file named hello.txt on the desktop, it must explicitly declare those permissions. Requests for other actions will be rejected. The extension store allows users to inspect required permissions before installation. A quick note, the permission system is inspired by Tori, the framework Kunkun is built on. Kunkun's permission layer mediates between extensions and the app, while Tori's permission system mediates between the app and the operating system. Extensions running within a browser environment suffice for many use cases, but some require more power and resource-intensive features. Let's say addition is a resource-intensive task, and you can run it in a separate process. It can be a Deno process, Python process, Node.js process, or any other runtime. Deno is an alternative runtime. It is Kunkun's default option for resource-heavy tasks. Users can optionally install Deno, unlocking advanced extension capabilities. Deno's sandboxing model requires explicit permissions for file access, environment variables, binary execution, and network access, making it more secure than unrestricted Node.js or Python. So why use Deno instead of shell commands alone? Let's consider video conversion. A simple ffmpeg command with the input and output file works, but creating a full-featured extension with options for bitrate, codecs, and aspect ratios requires more logic. You will need to construct the entire command within your extension. Libraries like Fluent ffmpeg for Node.js simplify this by providing JavaScript-based APIs to construct complex ffmpeg commands, execute them, and handle progress callbacks. Instead of rewriting these libraries for the web, Kunkun allows you to run them directly with Deno, leveraging its compatibility with Node.js APIs. However, communicating between the main thread and Deno process introduces challenges. Initially, I used shell arguments and pipe-based communication, standard in, standard out, and standard error. But this added unnecessary complexity. Developers will spend more time parsing arguments than building features. To simplify this, I created KRPC, a custom bidirectional remote procedure call protocol inspired by JSON RPC and Comlink. It facilitates communication between the extension's main thread, the Deno process, and the desktop app. It also supports HTTP and WebSocket communication resembling TRPC. If you're interested, I can make a video about it. In case you're unfamiliar with RPC, Remote Procedure Call, allows a program to execute a procedure in a different address space as if it were a local function, simplifying the inter-process communication. In Kunkun, the Deno process can expose functions for the extension's main thread to call, and vice versa. The bidirectional communication enables, for example, the Deno process to access extension's data store. Here's an example. The Deno process exposes a convert video function using Kunkun's API package. The extension's main thread uses Kunkun's shell API to create an RPC channel with TypeScript file paths specifying the permissions and the expected API interface. Although Deno permissions are written here in TypeScript, the same permissions used here also has to be declared in manifest package.json file. Otherwise, requests will be denied. Once the channel is established, the main thread can call convert video as if it were a local function. KRPC supports all JSON serializable JavaScript data types and even callbacks, making it powerful and flexible for extension development. Thanks for watching. I hope you found this architecture breakdown insightful.